Okay, so welcome back to this next video in which we are discussing calcium signaling. Okay, right, so we're in the process of discussing effectors of calcium signaling. Okay, and the first effector that we're talking about is CAM kinase 2, or the calcium calmodulin dependent kinase 2. Okay, now we've discussed that CAM kinase 2 is not directly activated by calcium. Rather, calcium is going to bind to the protein calmodulin to form calcium calmodulin complexes, and then the calcium calmodulin complexes are going to activate CAM kinase 2 enzymes. Okay, now, we've discussed how CAM kinase 2 doesn't exist as the individual monomer within cells. Rather, it exists as this dodecamer, which I'm just going to draw out again here. Okay, so what happens then is you assemble 12 CAM kinase 2 monomers together into this dodecamer, and the way you do it is by creating these two rings of 6 and then stacking them upside down relative to one another on top of each other. Okay, so here is one ring of 6 hub domains of CAM kinase 2s, okay, all stuck together to make one ring of 6 CAM kinase 2s, and then the ring on the bottom will be oriented upside down relative to the ring on top. So basically you've taken this, copied it, flipped it upside down, and then stuck the two of them together. Okay, right, and I will colour in this dodecamer of hub domains here in blue once again. Okay, so we then discussed that, excuse me, each of the CAM kinase 2 monomers within this dodecamer can be in one of two inactive states prior to the arrival of the calcium calmodulin complexes. Okay, so there is not just one inactive state, there are multiple inactive states. Okay, so we've discussed that there is this inactive state which is the closed inactive state, which I'll show here. Okay, and in the closed inactive state, the autoinhibitory domain is held very close to the hub domain. Okay, and then of course the catalytic domain of the CAM kinase 2 monomer here will be attached to the autoinhibitory domain and therefore will not actually be functional, okay, because the autoinhibitory domain is sitting within its catalytic site, and therefore it's not actually capable of phosphorylating any serine and threonine residues. Okay, so here is the catalytic domain here in red. Okay, right, so that's one of these closed inactive state CAM kinase 2s, okay, and basically it is not actually even activatable by calcium calmodulin complexes, okay, and the reason is that to activate CAM kinase 2 monomers, calcium calmodulin complexes need to be able to gain access to the autoinhibitory domain here in turquoise, okay, so that they can bind to it and make it release the catalytic domain. Okay, in this closed state where the autoinhibitory domain is held so closely to the hub domain, basically the calcium calmodulin complexes just can't get access to it. Okay, so the closed inactive state for CAM kinase 2 is inactivatable basically. Now let me show the other inactive state that calcium calmodulin kinase 2 enzymes can be in, which is the open and activatable state. Okay, so once again it is an inactive state, so the catalytic domain here is bound to the autoinhibitory domain. Okay, but now that autoinhibitory domain is not pressed up against the hub domain this time. Okay, and therefore it is available for the binding of calcium calmodulin complexes. So here's the catalytic domain in red. Okay, and then underneath that we have the autoinhibitory domain which is bound to it. Okay, so this is the open inactive state, okay, and calcium calmodulin complexes can gain access here, bind to that autoinhibitory domain, and cause the autoinhibitory domain to release the catalytic domain. Okay, so the open state is the activatable state. Now, all of the CAM kinase 2 monomers in this dodecamer will be moving between being in the closed inactive state and being in the open inactivated state. Okay, so you've always got some of the CAM kinase 2 monomers in the closed inactive state and some in the open inactive state in any dodecamer. Okay, now what does that mean? What's the significance of this? Well, it means that when you actually generate calcium signals in the cytoplasm of the cell, and therefore you generate calcium calmodulin complexes, you can't actually activate all of the CAM kinase 2 monomers in a dodecamer. Okay, you're only going to activate those that are in the open state. The closed state ones are going to be immune to the calcium calmodulin complexes, basically. Okay, so not all of the CAM kinase 2 monomers in a dodecamer of CAM kinase 2 are actually going to be activated at one time with one calcium signal. Okay, and this is what's going to be incredible and allow us to have a different response of the dodecamer to higher frequency calcium waves, and that will become more apparent in a moment. So firstly, let me start by telling you about how calcium calmodulin complexes then activate CAM kinase 2 monomers in a dodecamer like so. Okay, right, so let's now suppose that calcium calmodulin complexes have been formed. So we've had a calcium signal, calcium calmodulin complexes are now being formed in the cytoplasm. What ends up happening is calcium calmodulin complexes combined to the autoinhibitory domains of these open inactivated state calcium calmodulin dependent kinase 2s. Okay, so let me now show this. I won't draw out the entire thing again. What I'll just draw is one of the individual monomers. Okay, but remember it is in the entire great dodecamer. Okay, so here is its hub domain, which I'll just colour in blue here. Okay, and now what's going to have happened to this CAM kinase 2 monomer is that it's going to have calcium calmodulin complex bound to its autoinhibitory domain. So here is its autoinhibitory domain, and here I will show the CAM kinase 2, the calcium calmodulin complex bound to it. Okay, so here is the calcium calmodulin complex bound to the autoinhibitory domain of our CAM kinase 2 monomer. Okay, and now what that causes is it causes the autoinhibitory domain to release the catalytic domain. Okay, so once the calcium calmodulin complex is bound to the autoinhibitory domain like this, it can no longer bind to the catalytic domain. So the autoinhibitory domain releases the catalytic domain here, and now the catalytic domain has its active site here free, basically. Okay, and now that active site is actually capable of phosphorylating serine and threonine residues on proteins. So this is the active state of a calcium calmodulin dependent kinase 2 monomer. Okay, so this is active. Right, so basically when you generate a calcium signal in the cytoplasm of the cell, you will form calcium calmodulin complexes. These calcium calmodulin complexes, and I'll just label this up as a calcium calmodulin complex here. Okay, these calcium calmodulin complexes will bind to the autoinhibitory domains of the CAM kinase 2 monomers in a CAM kinase 2 dodecamer rather, that are in the open inactive state. Okay, and it will cause them to move from being in the open inactive state to being in this actual active state, where the catalytic domain has been released from the autoinhibitory domain and is now free to catalyze the phosphorylation of serine and threonine residues within proteins. So you will activate a subset of the CAM kinase 2 monomers in a CAM kinase 2 dodecamer, that subset that were in the open inactive state originally when the calcium signal occurred. Okay, right. So that's all fantastic, but how does this actually lead to these things being able to respond differently to different frequency calcium signals, basically, different frequency calcium waves? Because that was the thing that we were really interested to see for calcium calmodulin dependent kinase 2, how it could respond differently to different frequencies of calcium waves. Okay, right. So basically, the principle here is that if you've got low frequency calcium waves, then you're only going to get a subset of the CAM kinase 2 monomers in a CAM kinase 2 dodecamer activated at each calcium signal. So at each calcium wave you'll get a subset of them activated, whereas the idea is at higher frequency stimulation you can end up getting more of them activated. Basically it can build up so that all of them are actually going to be activated, and I'll explain exactly how this occurs. So to understand this we need to know something about the memory property of CAM kinase 2 dodecamers. Okay, so what is meant by the memory property of CAM kinase 2 dodecamers? So basically this memory property is all about the fact that CAM kinase 2 monomers in the CAM kinase 2 dodecamer can remain active, can remain in this active state even once the calcium signal has gone. Okay, so once calcium's gone, okay, the calcium calmodulin complexes have gone, okay, some of these CAM kinase 2 monomers in the CAM kinase 2 dodecamer can remain active even once that's gone, okay, and that's a memory of the calcium signal basically. Now I want to explain to you how this actually occurs. Okay, so what this relies upon is neighbours in the CAM kinase 2 dodecamer both becoming active at the same time. So let me now add another CAM kinase 2 onto my picture here. Okay, so here comes another hub domain here. Okay, and this one is the neighbour for this one here. Okay, well, one of its neighbours, of course it will have a neighbour on the other side as well, but we're using this one here. Okay, now, if both these two neighbours end up getting activated in a same calcium signal, okay, so when you form calcium calmodulin complexes, it just so happens that both of these were in the open inactive state initially before the calcium signal arrived, and then when the calcium signal arrived they therefore both got activated. So let me just draw this. So here is this other one now in this active state now. There's its autoinhibitory domain, and here is its catalytic domain squashed in here, okay, which is now free of the autoinhibitory domain. So I'll just colour it in. Okay, so here's the autoinhibitory domain in turquoise here, okay, and here's the catalytic domain in red, okay, and we've then got a calcium calmodulin complex bound here, okay, which is the reason it's in the active state here. Okay, so basically if you get neighbours in this CAM kinase 2 dodecamer getting activated in a single calcium signal, then what can happen is these two neighbours can end up giving each other the memory property. Okay, now how does this work? Well, remember these catalytic domains, they are serine-threonine kinases. They phosphorylate serine and threonine residues within proteins. It turns out that there are phosphorylation sites in these autoinhibitory domains that can be phosphorylated by the catalytic domains. Now, the catalytic domain of one CAM kinase 2 monomer is not capable of phosphorylating its own autoinhibitory domain. However, it turns out that the catalytic domain of a CAM kinase 2 monomer in the dodecamer can phosphorylate the autoinhibitory domain of its neighbouring CAM kinase 2 dodecamer. So basically this one here can phosphorylate the autoinhibitory domain of its activated neighbour, and it's really important that this neighbour needs to be in the active state for this to occur. Okay, it doesn't occur if its neighbour is in the inactive state. Okay, so if its neighbour is also in the active state, it can phosphorylate its autoinhibitory domain, and similarly this CAM kinase 2's catalytic domain here can now phosphorylate its neighbour who's in the active state's autoinhibitory domain here. Okay, right, so if you get CAM kinase 2 monomers in the CAM kinase 2 dodecamer being activated at the same time in a calcium signal, then they can phosphorylate each other's autoinhibitory domains. And now, what does this mean? This means that even once the calcium signal goes, okay, so let's say the calcium goes back to the normal 100 nanomolar, therefore calcium calmodulin complexes vanish from the cytoplasm, they return to apocalmodulin. So these calmodulin molecules will break off these autoinhibitory domains. Okay, even once that occurs, these CAM kinase 2 monomers in this CAM kinase 2 dodecamer remain active now. The phosphorylation does the same thing as the calcium calmodulin complexes, basically. It keeps them in the active state. So they remain active even once the calcium signal has gone. That is called the memory property of CAM kinase 2. Okay, because it is remembering the calcium signal. Okay, they remain active even once the calcium signal is gone, so it's remembering the calcium signal that occurred, basically. Okay, right. Now, these will remain active for a few seconds afterwards, okay, until enzymes in the cytoplasm remove these phosphate groups from these serine and threonine residues in the autoinhibitory domain. Then they'll remain active. Of course, once the phosphate groups have been removed, then eventually the CAM kinase 2 catalytic domains will then rebind to the autoinhibitory domains, and they'll return back into inactive states. Okay, now, why then does this lead to CAM kinase 2 dodecamers responding differently to low frequency and high frequency calcium waves? Well, let me try and explain this using some graphs. Okay, graphs are the best way to do this. So let's have time on the x-axis here. Okay, and let's have how many CAM kinase 2 monomers in the CAM kinase 2 dodecamer are active. Okay, so this is activity. Okay, so if you we would have 12 at the top here, that's the maximum, and we'd have 0 down at the bottom, and then we've got all the other numbers in the middle, basically. Okay, now, if we start off delivering low-frequency calcium waves, okay, so let's say we have a calcium wave every half a minute, okay, every 30 seconds, okay, so that's quite a low frequency of calcium waves, okay, so 30 seconds there, and then we'll have 60 seconds here, okay, then what will happen? Okay, well, every time you get a calcium wave, and let's say we have one at 0, one at 30, one at 60, every time you get a calcium wave, you'll get some of your CAM kinase 2 monomers in the CAM kinase 2 dodecamer becoming active. Not all of them, however. Remember why it's not all of them, okay, because some of them will be in this closed inactive state when the calcium signal occurs, and therefore will not actually be activatable. Okay, then this will gradually go down. Okay, so once the calcium signal is gone, then many of the CAM kinase 2s will inactivate. You'll have some that have done the memory property and therefore will remain active for longer, but if you wait 30 seconds, those will go as well, so you'll be back down to 0 by the time that the next calcium signal occurs, and then you're back in square one. Okay, we're getting another calcium wave, but you've got no CAM kinase 2s already active in the CAM kinase 2 dodecamers, okay, and therefore you're just back to square one, so the exact same thing will happen again. Okay, and you'll only ever get this sub-maximal number of CAM kinase 2s active at any one time, basically. Okay, so that is what will happen if we have a low frequency of calcium waves. We're only going to get a sub-maximal number of CAM kinase 2 enzymes active at any one time. Okay, so this is low frequency. Okay, let's now imagine what happens if we hugely step up the frequency of the calcium waves. Okay, so let's say we now take them down to having calcium waves every, let's say, 5 seconds rather than every 30 seconds. Okay, then what you can imagine is we'd be firing another calcium wave at this point here, okay, before, and maybe I'll just make it a little bit more extreme there, so we'll take 5 seconds to there, okay, so that it has started to go down at least, okay. So now what will happen is when the next calcium wave occurs, some of the CAM kinase 2s will still be in the active state, okay, because of the memory property. Okay, so because of the memory property, some of them will still have phosphate groups attached to their autoinhibitory domains, and therefore will still be on when you fire the next calcium wave. Okay, and then what will happen is when you fire this calcium wave, you'll then recruit a certain number of the other ones that were in the inactive state, and then it starts to go up, basically, And then when you fire it again, you can see that it starts to build up to the point that you can actually get the CAM kinase 2s getting the maximal number in the dodecamer actually active at any one time. Okay, so the basic principle is that if you fire high frequency of calcium waves, okay, then you will be firing another calcium wave before all of the CAM kinase 2s in the CAM kinase 2 dodecamer have returned back to being in the inactive state, okay, and therefore when you fire the next calcium wave, you will gradually be building up the number of CAM kinase 2s that are active at any one state, basically. At any one time, okay? So, if you have a high frequency of calcium waves, then you can gradually recruit more and more CAM kinase 2s in the CAM kinase 2 dodecamer and get to the point where you can actually have all 12 CAM kinase 2s active at any one state. Now, of course, in between the calcium waves, it will drop back down a little bit. Some will be lost, but then you'll put them back into the active state when you fire another calcium wave. So you'll all the time be bobbing back up to 12 and then going back down a little bit. Okay, so that basically is the principle of how one low frequency of calcium waves can cause a certain response in the kinase 2 dodecamers, and then a different frequency of calcium waves, the high frequency of calcium waves, can then cause this different response in the CAM kinase 2 dodecamers. So basically, at low frequency, you're only getting a sub-maximal number of CAM kinase 2 monomers in the CAM kinase 2 dodecamer active at any one time, okay, with any one calcium spike. Okay, whereas at a high frequency you can gradually build up to getting a much greater number of CAM kinase 2 monomers in the CAM kinase 2 dodecamer being active at any one time. And the thought is that these CAM kinase 2 dodecamers, which have all of their monomers active at one time, might have very different effects within the cell than CAM kinase 2 dodecamers, which only have a few of their CAM kinase 2 monomers active at any one time. So basically, this might be an example of how the cell responds differently to different frequencies of calcium waves propagating across the cell. Okay, right. So that now is CAM kinase 2 finished. Okay, and that is really the only example that I'm going to discuss of an effector that is actually capable of decoding different frequencies of calcium waves. Okay, the next effector that I want to talk about is the protein kinase C enzymes, and now we will get to see the signaling roles of the diacylglycerol, which was the other product of the breakdown of phosphatidyl inositol 4,5-bisphosphate by phospholipase C enzymes. Okay, right, so let's now talk about protein kinase C enzymes. So, protein kinase C enzymes, there is a massive great family of protein kinase C enzymes. Like phospholipase C enzymes, it's not just one enzyme. There's a family of protein kinase C enzymes, and they're all regulated by different things. Now, the ones that we're going to be interested in are the ones that are regulated by calcium, basically, because we are talking about calcium signaling. Okay, and the protein kinase Cs that are regulated by calcium are known as the conventional protein kinase C enzymes. Okay, right, so firstly let me just take a step back and say protein kinase C, it's often abbreviated down to PKC. It is a family of serine threonine kinase enzymes, okay, and the reason it's called protein kinase C is because they are regulated by calcium. However, it turns out that not all of the members of this great family are actually regulated by calcium. We're going to talk about a subset of the great family of protein kinase Cs, which are called the conventional protein kinase Cs, okay, which for short are abbreviated down to the CPKCs. So conventional protein kinase C is abbreviated down to CPKC. Okay, and the CPKC family contains 3 different protein kinase C enzymes, okay, which are the protein kinase C alpha enzyme, the the protein kinase C beta enzyme and the protein kinase C gamma enzyme. So protein kinase C alpha, protein kinase C beta, and protein kinase C gamma. These are the three members of this conventional family of protein kinase C enzymes that are all going to be regulated by calcium, and that's why we're discussing this family. Other families, such as the novel and atypical protein kinase Cs, they're not regulated by calcium, which is why we're throwing them aside. Okay? Right then, so let's discuss the conventional protein kinase Cs then. Okay, so conventional protein kinase Cs, unlike CAM kinase 2 enzymes, they actually do have a binding site for calcium, so they bind calcium themselves and they respond directly to that calcium. They don't require calcium calmodulin complexes to bind to them. Okay, so conventional protein kinase Cs then, they are usually floating around in the cytoplasm. However, once they have got calcium bound to them, they will relocate to the underside of the phospholipid bilayer. Okay, so let me firstly discuss the special domain that protein kinase C enzymes of this conventional class of protein kinase C have in order to bind calcium. And this special domain is called the C2 domain. Okay, right, so this is my picture of the conventional protein kinase C here. Here's its active site, which can phosphorylate serine and threonine residues. And here is this special domain, the C2 domain, okay, which is capable of binding calcium ions and will change the behavior of the conventional protein kinase C enzyme once it has calcium bound to it. Okay, so let me just discuss C2 domains, because we are going to see more C2 domains later on. Okay, so C2 domains then, they are a type of domain that you find in many proteins, not just conventional protein kinase Cs. We will see them later in the synaptic protein. Okay, and they're another domain which is capable of binding to calcium ions. Okay, so we've seen EF-HAN domains, which are a broad domain found in many different proteins, such as STIM1 and calmodulin are the two examples we've seen, which is capable of coordinating calcium ions. These C2 domains are another example of a domain found in many different proteins, which is capable of binding calcium ions. And basically, the structure of a C2 domain is a beta sandwich. Okay, so I just want to explain to you what is meant by a beta sandwich. Okay, so basically a beta sandwich is just two beta sheets that are put parallel to one another. So let me just show you this. So a beta sheet then is made up of loads of beta strands all running in parallel to one another. So this is a beta sheet here. And basically, just to make a beta sandwich, it's really simple. All you do is get another beta sheet and stick them on top of each other like two pieces of bread making a sandwich. Okay, so that's why it's called a beta sandwich. It's a sandwich, effectively, made out of beta sheets rather than bread. So here's one beta sheet, and here is another beta sheet. Okay, so to just make this absolutely crystal clear, these beta sheets will consist of beta strands of the peptide, like so potentially. Okay, so here is the beta strands going up and down that beta sheet, and then suddenly the polypeptide will move over to the other beta sheet, and then you'll make this other beta sheet. Now, usually, in reality, when you have C2 domains in proteins, they have a much more complicated structure than this. The polypeptide moves between one and then goes into the other, moves back and back and forth, basically. It's really complicated. But this gets across the essential principle here, that you have these two beta sheets opposed to one another in parallel, and that's what is meant by a beta sandwich. Okay, so these C2 domains, then, they are these beta sandwich structures. How do they bind calcium? Well, where did calcium bind in the EF-HAN domains? Okay, it bound in those little turns between the E and the F helices. And similarly, in C2 domains, it's going to bind in the turns, basically. Okay, these loops between beta strands in beta sheets, basically. So these loops, I'll just highlight some of them up here. These loops between the beta strands that make up the beta sheets. These are the things which might just be able to coordinate calcium ions. So some of them will have negatively charged residues in, aspartate and glutamate residues, and then they will be able to coordinate calcium ions in their middle, basically. Okay, and when one of these loops is capable of coordinating calcium ions, or rather a calcium ion, it's called a calcium binding loop. So I want to stress that not all of these loops between beta strands in this beta sandwich structure will actually be calcium binding loops. A few special ones, a few select few, will actually be capable of binding a calcium ion, okay? And those ones are going to be called the calcium binding loops of the C2 domain. Okay, right, so C2 domains generally they have 2 or 3 calcium binding loops within them, okay, and therefore they can coordinate 2 or 3 calcium ions depending on how many calcium binding loops they have. I don't actually know the exact number of calcium binding loops that are present in the C2 domains of each of the conventional protein kinase Cs, but it will be around 2 or 3. Okay, so the essential principle then is that these conventional protein kinases, they have this special domain, this C2 domain, which is capable of binding to 2 or 3 calcium ions, okay, and prior to the binding of the calcium, so prior to calcium going up in the cytoplasm, when you've got 100 nanomolar calcium, there's not going to be any calcium bound to these C2 domains, okay? Prior to the binding of calcium, the conventional protein kinase C is floating about quite happily in the cytoplasm of the cell. Okay, now what's going to happen is when you generate a calcium signal, so when calcium goes up in the cytoplasm above 100 nanomolar, what will now start happening is you're going to get calcium ions binding onto that C2 domain. Now what's that going to result in? Well, that's going to result in the C2 domain getting a positive charge, basically, okay, because calcium ions carry a positive charge. So what that then allows the protein kinase C enzyme to do is it allows it to associate with the phospholipid bilayer, because remember, phospholipids in the phospholipid bilayer, their heads are generally negatively charged, okay? They have a phosphate group at their head, and that phosphate group has a negative charge, okay? So now the positively charged C2 domain can bind to the negatively charged heads of phospholipids. Specifically, the C2 domain loves to bind to a certain type of phospholipid called Phosphatidyl Serine. Okay, and I'll just talk you through the structure of Phosphatidyl Serine. Now, this won't take us that long because we already know what that prefix phosphatidyl means. Okay, we've seen that in phosphatidyl inositol 4,5-bisphosphate. So, Phosphatidyl Serine then. Okay, so Phosphatidyl serine is another membrane phospholipid. It's not the most common membrane phospholipid, but it is a membrane phospholipid that's in the cell membrane, okay, which is based on the structure of phosphatidic acid. Okay, so let me firstly just draw the phosphatidic acid structure once again. Okay, so here is my phosphatidic acid structure picture. So here is the glycerol molecule. Here are the 2 long-chain carboxylic acids anchoring us in the hydrophobic core of the phospholipid bilayer, and here is that phosphate group coming off the alcohol group of the 3rd carbon of the glycerol molecule. Now, to convert phosphatidic acid into phosphatidyl serine, you then need to add something onto the phosphate group of the phosphatidic acid molecule. And specifically, you need to add on a serine amino acid, basically. So serine has an alcohol group which can also attach onto that phosphate group of the phosphatidic acid molecule, just like inositol could, basically. Okay, and that now creates us a molecule of phosphatidyl serine. So I'll just represent the serine molecule as this rectangle here in blue. Okay, right. So basically, this is a normal component of the phospholipid bilayer of cell membranes, okay, and C2 domains absolutely love to bind to phosphatidyl serine. So the C2 domain of protein kinase C, once it's got calcium bound to it, is going to come up and associate with phosphatidyl serine molecules in the leaflet of the phospholipid bilayer. And what this is going to do is it's going to relocate the conventional protein kinase C enzyme, so that now it's located attached to the underside of the phospholipid bilayer here. Okay, so I'll show this like so. So here is our C2 domain here in red, okay, which will now be bound to a phosphatidyl serine molecule in the inner leaflet of the phospholipid bilayer. Here's the rest of our conventional protein kinase C enzyme with the active site here. Okay, now it's been relocated to the underside of the phospholipid bilayer. Now that doesn't activate it yet, that just relocates it. The other thing that conventional protein kinase Cs now need to activate them is that other product of the breakdown of phosphatidyl inositol 4,5-bisphosphate. Okay, and remember that other product stayed within the phospholipid bilayer. So when we initially broke down PI45P2 into IP3 and what else was that other product? That was diacylglycerol, DAG. Okay, and diacylglycerol that's now in the phospholipid bilayer when we activated those phospholipase C enzymes, that is the other essential ingredient for activating these conventional protein kinase Cs. Okay, so if you like, the calcium signal translocates the conventional protein kinase C up to the underside of the phospholipid bilayer so that then diacylglycerol can do the activation, basically. Okay, and now our conventional protein kinase C is going to be active. Okay, and what it will now go on to do is phosphorylate serine and threonine residues in a whole bunch of targets, just like CAM kinase enzymes can, and therefore it can change the behavior of a huge number of different proteins. Okay, so that's another really important target of calcium signaling. Okay, right, so we'll call it there for this video, and in the next video what we'll talk about is the effect of calcium on the mitochondria, so on the respiratory reactions.